Hi, I'm Ben-Yaakov. This presentation is entitled Losses of Power Inductors in PWM Converters. There is a disclaimer here that the components and the design tools that I'm showing in this presentation are for educational purposes only. There is no recommendation or endorsement implied here. And also, I'm not affiliated with any of the companies that are going to be mentioned in this video. In this presentation, I'm going to, first of all, give an introduction to the inductors and PWM converters, very simple, and then looking at the reasons for losses in power inductors, which can be broken down into RDC losses, RAC losses, and core losses, and then discuss what can be found at data sheets regarding losses, and then simulation tools that are offered by manufacturers that include losses. Inductors are used widely in PWM converters as part of the topology, and here I'm showing a synchronous buck converter. There are two transistors which are turned on and off synchronously, and then we have the inductor, the filter capacitor, and this represents the load. And you can look at the inductor as part of a filter that actually is filtering out the square wave that is generated here at the midpoint due to the switching of the two switches and smoothing it out to obtain a DC voltage at the output. I'm going to use this simulation circuit to discuss some of the issues of this presentation. Traditionally, the losses of power inductor were primarily attributed to the DC current. And here is a typical curve that you'd see in many application notes and data sheets. The temperature rise as a function of the DC passing through the inductor. And this is due to the fact that the inductor includes a RDC, that is a resistive part, and therefore as you have current flowing through it, then of course there is a power dissipation and temperature will rise. However, we know that aside from the DC resistance, we have the so-called RAC resistance, which is due to the fact that we have skin and proximity effect. This is actually from a TDK datasheet. Here we see the RAC going up. I'm not sure that it includes proximity, but anyhow, clearly we see a major change in the resistance, RAC resistance, as you go to higher and higher switching frequency, and this will be, of course, related to the ripple. So typically, we're going to have a ripple current through the inductor, which has a AC component, of course. Then we have the DC component, the average, and the total power dissipation of the inductor will be the DC part square, the current, times the RDC, plus the AC part times the RAC, which is, of course, a function of frequency. Now, the point is that if you have a commercial inductor, you don't know anything about this. You don't know anything about how does it change, unless, of course, you have a information that is provided by the vendor. There's no way you can tell from the component itself. So the issue here is, how do we estimate the total loss and the temperature rise of the inductor? In circuit simulators like LT-SPICE that I've shown earlier, you can actually pick a commercial inductor. So here is a commercial inductor. This is a Coilcraft 27 microhenry, and here are the parameters that they are showing. 27 microhenry. Peak current, really it's not that important, but then series resistance, very important, 45 milliohms, and then there is a parallel resistance, 2.5 kilo ohm, and in this particular case, the parallel capacitance is 0. So the model is actually looks like this. This is the 27 microhenry, the inductor, the RDC, then 2.5 kilo ohm, and in this particular case, they are not providing information about the parallel capacitor, which is, by the way, very important. So the question is, of course, is this now also taking into account the RAC? It doesn't say here, so let's explore this question. First of all, we know you can get in LT-SPICE the power dissipation of a component by pointing to the component like the inductor and then Control plus a right click. This will bring you this product. This is the voltage times the current of this particular element. So here I'm showing a simulation result of the circuit. Let me go back of this circuit running at 100 kilohertz, 80 volt input, 0.5 duty cycle, and here is the load. And here are the results. This is the midpoint, the voltage at the switching node. We have the inductor current, and this is the product that we got from the simulator of the inductor current times the voltage across the inductor, okay? So this is the product here. Now the average of this is the power dissipated. So let's go step by step. First of all, let's have a look at the current. I see that the average current is 4.9 and the RMS, the total RMS of this waveform is 5.1. So the contribution of the ripple is not very large here. And here we have the product. Now, I did here a very simplistic calculation, assuming that our AC is like our DC. That is assuming that this simulator does not take into account our AC. In this case, I just take the RMS square times our DC, and I'm getting that the power dissipation should be 1.17 watt. Now, I'm looking at the average of this product, which is a measure of the power dissipation or power loss based on the simulation, and I'm getting 1.4. So it's a bit higher. So it seems that it's indeed taking into account losses due to the AC, to the higher frequency. But it's hard to tell because they are pretty close here. So what I did, I ran the same circuit at 500 kilohertz. Now in this case, of course, I had to adjust the voltage so that I'll get about the same ripple and about the same DC current. And lo and behold, I see that in this particular case, the product of the voltage times the current, the average of this product, is 5 watts. So indeed, it seems that this simulator is taking into account the frequency effect and the RAC for this particular model that I've picked up. I don't know about other models. Now, I don't know if this is only for the windings or does it take into account the core losses. I have no idea to tell, but it definitely takes into account the frequency change and the RAC of the circuit. Now, in order to probe a little bit more into it, I ran a AC sweep on the inductor, and in this case, I expect to see that the phase of this element, of this inductor, will change with frequency. Pure inductor has a 90-degree lag of the current with respect to the voltage. This is a voltage source, AC voltage source. So what I'd expect to see that as the frequency goes up, the phase should change. And indeed, this is exactly what I see. I see that the impedance, or the current, let's start with the current. This is the current of the inductor is going down. This is because the impedance is going up. That's okay. But I also see that there is a change in the phase, okay? It's starting with about minus 90 degrees, as I would expect. It's here from 100 kilohertz, so at lower it'll be closer to 90. But then it moves up to 8 minus 86.1 quite a bit. Okay, now using this phase shift, I can actually calculate the RAC. And this is done by, first of all, finding what is the impedance. The impedance is the 1 volt excitation and about 5 milliamp current here. It's about 5 milliamp, okay? So it's about 200 ohms. So our AC will be this Z times cosine of this phase, and this comes to be 13.6. That's a lot. So remember that our DC was only 45 milliohm. So we definitely see here the effect of the frequency on the resistance. So I did something more here. I've injected also a DC current. And this is done by adding a DC offset to this source, to the AC source. And indeed, I can run an operating point test, and I see that this inductor IL2 is 22 amp. So this inductor should be close to saturation, because that's quite a bit of a current here, okay, 22 amp. But if I run it, I don't see any difference. This is exactly the same what we got before. Like at 100 kilohertz, it's a little bit lower than 60 milliamp, and this is exactly what I got here. So it seems that at least in the AC run, it does not take into account the change of the inductance as a function of the current. I don't know about transit, I haven't tried it. So this is something to worry about, that perhaps it does not take into account the change of the inductance as a function of the bias current. Now what about core losses? Well, most inductors are built around a ferrite or some powder iron core, and the losses are a function of the magnetic flux density. This is for a given material, 3F3 of Ferrous cube, and we see here this is the magnetic flux density, the amplitude, and then a function of the frequency, we get the loss per volume, and this is very typical of all ferromagnetic material. So once the inductor is built around the ferromagnetic material, there are some core losses which are a function of this B. Well, we don't know anything about the B in a commercial unit, but we know that starting with Faraday law, that the flux itself is a function of the integral of the voltage. And also, if you look at B, it's mu times H, and H is Ni over Le. Le is the magnetic path. So B is related to the current, the ripple current. So in fact, if I take the integral of V, then of this midpoint, or voltage across the inductor more accurately, I see that this is basically like the ripple current. So the ripple current sort of tells us something about the B, but we are missing all these constants. So we cannot tell by just examining the component without actually very rigorously testing it, what are these constants, so therefore we can't tell about the core losses. So we do need information from the manufacturer for that. Now in the regular data sheet, you don't see anything of this nature. I mean, you see microhenry, you see RDC, you see what is the saturation current, but you don't get information about losses. However, recently, since this issue is important, we see more and more vendors providing tools that you can not only test some simple things, but also look at the losses. So here is one example. Again, there are other companies who make it or make similar simulator. I'll show another one in a minute. And here's the Coilcraft panel. It shows the converter, the topology, and then you can put in parameters for the operating point. And I've put here parameters which are close to the operating point of the converter that I've shown before. Okay, so we'll get a feeling of the same thing. And this is about 50 or 60 volt. This is the range. We have a 5 amp, 100 kilohertz. And here is what I'm getting. The simulator gives a suggestion of various cores that would do the job for this particular application. And among other things, you see here the total loss, okay? So here is 2.6, this is milliwatt, 2.6 watt, half a watt, etc. So you can pick your inductor per, for example, the losses that you have here. By the way, it is very interesting to see that here are two cores. This one is sort of a potted core, like a shielded core. Here one is open. There is no closed ferrite or some other ferromagnetic around the coil. And lo and behold, you see that although this is about the same inductance, and in fact the DC resistance of this coil is higher than this one, total losses are here much lower than this core. That's very interesting. I was not aware of that the differences are so large. So this is very important information that you can pick up, assuming, of course, that this information is correct and it has been checked against experiments, which I don't know. But anyhow, it's one big step forward that we can get information about the losses. Okay, so now you can pick up one of these. For example, I've picked up this first one, and you get this panel, which shows you more information. For example, it shows you the part of the AC losses. This is core plus winding AC losses. This is the black bar here, while the DCR, the DC resistance, is only this part here for this particular inductor at this 100 kilohertz and this operating point, of course. We see also the reduction of the inductance as a function of the DC. This is very typical. We see it in just any data sheet, of course. And then there's more information here. For example, the loss as a function of V in, if the V in changing from 50 to 60, the temperature increase as a function of IDC. We are working at 5, so it's really moderate here. And then also it shows the loss as a function of switching frequency. Well, it seems that it's going up. This is not very accurate because what it assumes that the amplitude of the ripple will increase with the lower frequency, therefore the losses will increase. But then you may go into DCM, and I don't know whether it takes into account the fact that you go into DCM. I guess it's assuming CCM all over the range. Anyhow, we are interested in one particular frequency. Here it is, and this is the losses that we get. As I've said, other vendors have similar tools, and here is the Worth tool, the Red Expert. And in this particular case, we have actually a synchronous buck converter. Again, you can put in the parameters and then choose one of the inductors that are offered or suggested, which I did. This is the red one. And you get some basic information, the change of inductance with DC. And by the way, this break here suggests that perhaps this is based on actual measurements, not just estimation, because this will be typical of experimental results, but I don't know, I'm not sure about that. And here is the increase in temperature due to the increase in, or as a function of the DC current. And then you get also the panel with more information, like the breakdown of the losses. This is the total loss, this is the AC part, and this is the DC part. Again, the AC part is much larger than the DC part, and this is a function of V in. It's not a big change, and also as a function of the frequency, and as we've seen before, also here we see that due to the increase in the ripple, you'll have supposedly higher losses, but again, I don't know if it takes into account that the system goes into discontinuous mode. So let me wrap up here with some comments. We see that the inductor's AC losses could be very, very significant. There's no question about that. And that some vendors and more vendors are providing detailed AC loss information, either directly or by simulation tour. I don't know how accurate are these simulators and how well are they tested against experimental testing, experimental result, actual testing. I would assume that it is. I don't know if each one of the inductors were probably sampled and tested, so the information given is very, very valuable. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.